they start off with saying, hey, do you remember graphing this? X minus 1 squared. In your transformations unit, do you see that that's a parabola? Just moved 1 unit to the right. So if you were asked to graph that with transformations, I'd go 1 unit to the right, draw my vertex, it opens up, there it is, with, I'm not labeling any points, so I know I would lose a half mark, but just the general picture, agree that that's what it would look like, okay? And if you were to graph it cubed, well, that's just our x cubed graph from transformations. Move 1 to the right. Oh, I want black axis. There we go. Moved 1 to the right. And you remember that your x cubed graph looked like this. More or less. Move 1 to the right. Okay. So what is happening now is, if we were thinking about this x cubed graph, x minus 1 cubed, would you agree that I could have written it like this? 3 times. And if I was solving for x-intercepts, well, this one would tell me an x-intercept of 1, 0. And this one would, it would tell me an x-intercept of 1, 0 again. And this one would tell me an x-intercept of 1, 0 a third time. So it actually is important how many times an x-intercept occurs. Here, we would say the x-intercept occurs twice, and so we would call it an x-intercept with a multiplicity of 2. We use the word multiplicity because it happens more than once. This one, we would say the x-intercept has a multiplicity of 3. Every example that we had done so far all had multiplicities of 1. The x-intercept only happened once, and it was pretty straightforward what happened when it happened once. But off to the side here, we are going to add the following notes. So, off to the side on page 44, or you can even do this at the bottom, you'll have enough room. If a graph has an x-intercept with an even multiplicity, so it has an exponent of 2, 4, 6, any even number is an exponent. The graph, and I don't know if this is an official math word, so I'm going to put it in quotation marks. The graph bounces off the x-axis. Do you see that that's what happens in a parabola? Right? Didn't it just bounce off the x-axis and head back up again? So we're going to find anytime we have a graph where you have an x-intercept that has a multiplicity that's even, happens 2, 4, 6, 8 times, it will always bounce off the x-axis at that time. And when you have an odd multiplicity, okay? So if the graph has an x-intercept with an odd multiplicity, there are 2 situations that happen. So we're going to sort of separate it into 2. The one that we have seen the most is that if you have a multiplicity of 1, the graph will go straight through the x axis. Just goes right through that point. Nice smooth line right through that point. But any odd number bigger than 1 and again, these are my words. You can either use the word bends. They really like it if you use flattens out. At the x-intercept. So actually, if we go back to chapter 3 and I would double check all of your x cubed graphs, you'd probably all lose some marks. Because, and even the one that I drew here, and I'm going to scroll up for a second, I'll come back. So if you want to finish this up, and I say the graph bends or flattens out at the x-intercept. Sometimes I draw the x-intercept and I actually draw a little tiny flat line there. And then I connect it to the rest of the graph. Because if you would have drawn an x cubed graph like this, which you probably did in transformations, technically you'd lose a half a mark on that one now. Because it didn't quite flatten out. I should draw my axes, have my x cubed graph, draw a tiny little flat line, and then connect from that side up, this side down. That's a better x cubed graph. It completely flattens out at that point. So we say bends because it really has to show a bend in the graph. This black one is still pretty smooth through that x-intercept. So it bends or flattens out. Now with this, we can graph even more complicated polynomial functions. And the nice thing in example 3, they saved you some time. They already factored it. So 3 could be much more complicated. If they would have started with an x to the 5 graph, you'd have to use synthetic division 3 times to factor it and finally get this as an answer. Okay? But here we got to be careful with the y-intercept. What happens when I plug in 0 for x? What do I get? This will be 1 to the 4, which is still 1. This will be -2. -2 times 1. I get -2. But I have to do the mental math to figure it out. Because it's not necessarily going to be, at this time it was coincidence. It still was the last number. But that was just a coincidence. The end behavior is a little bit tricky in these ones if it's already factoring. You have to look at this and say, if I multiplied it all out, does it make sense that the x to the 4 would have an x to the 4? And this one has an x. And so if I did an x times an x to the 4, this is going to have an x to the 5 plus something. So my end behavior is going to act like a line with a positive slope. Start down there, end up there. But what's really nice is that because it's already factored, I can list all my x-intercepts. I have an x-intercept at -1, 0, and I have an x-intercept at 2, 0. But now underneath these, I'm just make a note that that one had a multiplicity of 4. This one had a multiplicity of 1. So now going to graph these. I know my y-intercept right here. 0, -2. I know my x-intercepts, -1, 0, and 2, 0. And I know my end behavior starts down here. So I know that I'm starting down here. Okay? Multiplicity becomes really important here because this multiplicity of 4 means when I get up to this one, I'm going to bounce off of it. When I get to this one, I'm going to go straight through. And this is a quite accurate graph. Even though we don't know how far it's going to go below, I just drew smooth through those points, and I get a really quite accurate graph. Calculus next year would say, you definitely need to find this minimum value to be super accurate, and you will be able to find that easily. If we go to B, negative g of x, just rewrite it. Negative out in front, x plus 1 cubed, okay, x minus 3. I am always super amazed, not in the good way, at how people struggle with their mental math of plugging in 0. So do it in your head. Plug in 0, tell me what the y-intercept is. I'll give you half of it. The x-coordinate is 0. You have to do the other half. Okay. Did you get positive 3? Okay. If you make a mental math error in your y-intercept, when you go to follow the rules with bounces and bends and straight through and end behavior, something will not work out. And you'll be like, I'm supposed to bounce, but then I'm supposed to go through my y-intercept way up here. How am I going to do that? So that probably tells you you made a mental math error. Okay? There's our y-intercepts. Now our end behavior, let's do that next. This also causes some mental math issues. End behavior. Is this an x to the 3x, the 4x, the 5x, the 6? What graph is this? How many x's would there be? Well, this x cubed would give me x cubed, and another x here, x to the 4. And then what's the coefficient in front? If you multiplied all of the first terms, and sometimes right? If I multiplied all of the first ones, you see that would be 1x to the 4, and there's also a negative out in front. This is going to be a negative x to the 4 graph. So my end behavior tells me it acts like a parabola. There's my end behavior. It's going to be going down in both of those directions. Then my x-intercepts. First one, -1, 0. Underneath that, I'm going to write multiplicity of 3. Next one, 3, 0. That one has a multiplicity of 1. So when I go to graph this, where's my y-intercept? My y-intercept at 0, 3. Label that point. X-intercepts -1, 0, and 1, 2, 3, 3, 0. Then on this graph, multiplicity of 3 at -1. It's got to flatten out, so I'm going to draw a little flat line here to start. and the multiplicity of 3, it's going to go straight through. Now my end behavior, it has to start down here. Connect to the one side of the flat node, go through the flat node, come back up, and this one straight through. If you accidentally got 0, -3, then you would bounce instead of flattening out, and you know you did something wrong. If you ever draw a graph and invent a new x-intercept, it's going to be catastrophic. You found all of the x-intercepts. This graph has no new x-intercepts. If you draw new ones, it's going to definitely take off at least 1 mark, maybe more. So if things don't work out, probably you made a mental math mistake somewhere. All right, questions to circle 9, 10, 11, and 12. And now you can do everything except for word problems on that take-home quiz.